TV channel. I'm Sulakshana Vagmare and today I'm going to take 12th standard physics. It is from Maharashtra State Board. Now let us start. Today our chapter is your 5th chapter, elasticity. Now in this chapter we will learn the property of elasticity of solids. All the rigid bodies are up to some extent elastic. You know that there are we can't say that there is perfectly rigid body or perfectly elastic body or perfectly plastic body. We will see all these property one by one. So let's see. This means that their dimensions can be changed, means the dimensions of elastic bodies can be changed by pulling, pushing, twisting or by compressing them. That is, when a helical spring is stretched or pulled gently from both the ends, the length of helical spring increases, and when we remove the force, the spring regains its shape. That means it regains its length. So this property of regaining its shape or regaining its original dimension after removing the force is the property of elasticity. Now similarly, we can pull the rubber cord. It will also show the similar property. That means after removing the force of pulling, the rubber cord will regain its shape. Now as soon as the forces applied at the two ends of the rubber cord are removed, it regains its original size and shape. So when a body is subjected to a set of balanced forces, set of balanced forces means the forces are from all sides or from any two sides but are equal and opposite in direction and acting at different points, or we may say that both are acting at the same point. So these balanced forces which do not cause any type of motion, that forces produces change in size or shape or both of the particle. Now some bodies undergo change in dimension, that is size, shape or both, easily, while some bodies are reluctant to undergo any change in dimension. Some bodies show permanent change in their size, shape or both after removal of applied force, whereas some bodies preserve their original size, shape or both after removal of applied forces. Now here in this para we saw three cases, means after applying balanced forces, the forces which are not causing any kind of motion, there are three chances. First, there will be change in the dimension of the body. Second, there will be no change, and third, there will be permanent change in the dimension of the body. So we will discuss these three cases, and for these three cases there are three properties of matter that we will see. So now let's see general explanation of elastic property and elasticity of a material. This is first property that we are seeing here. So now let's see, when an external unbalanced force is applied to a body, it gets deformed due to relative change or displacement of molecules. That means suppose I have some particle or I have some matter. As you know, matter is made up of molecules, and when we apply the force, the molecules get displaced, means they change their positions. So because of this relative displacement of molecules, relative displacement means they are changing their position from original position. So relative displacement. So because of this relative displacement of molecules, forces are developed within the body which aim to oppose the deforming forces. So if the deforming forces acting on the body are removed, the body is acted upon by internal elastic forces developed within the body which try to restore its original dimension. Now here the internal force, that is opposing the deformation, you learn about this property. We can say it can be mass, can be inertia of a body and all. So because of this, there will be the displacement or change in the dimension of a body, but till that, whenever there is force, after removing the force, because of this restoring force, the body will regain its shape. For example, here given as paused. The bodies which do not return all its original dimension after removal of deforming forces are plastic, that is inelastic bodies. Bodies or materials, for example, putty, dough, lead, plasticine, clay, etc. Here, second example is given. That means there are some bodies which show deformation when force is applied, and even after the removal of force, they regain some deformation. Means they don't regain their original dimension. They have some changes in their dimension from original dimension. So these kinds of bodies are plastic bodies. Now elastic bodies are those bodies, those regain their shapes or dimensions completely after removal of forces. And the third type is of rigid body. In the rigid body, the molecules or the particles of a matter are tightly bound to each other, so that even after application of large amount of force, they don't show any movement. Means there is no displacement at all. So that's why they are called rigid body. That means they don't show any kind of displacement. So here is the definition of elasticity: the property by virtue of which material bodies regain their original dimensions. Dimension may be size, shape or both after removal of deforming force is called elasticity. This is the important definition. Now let us see origin of elasticity. Now let us see the origin of elasticity, means from where elasticity arises. Now solids consist of atoms, that you know, and molecules situated at definite positions in equilibrium state. Here we are taking equilibrium state, means there is no change in any kind of dimension or temperature, external environment, external forces and all. Now when force is applied to a body, the atoms in a body are displaced from their equilibrium position. Internal elastic forces are set up within body which try to restore the equilibrium position of atoms. Here externally means, suppose we are considering only one particle of a material. Let us consider we are applying external force to that particle. So when we are applying the force, at same time there is a restoring force developed which is opposing the motion of the particle. So when we are applying the force, there will be displacement of particle, but as soon as we remove the force, the particle will regain its original position because of this restoring force. Now internal elastic forces which are set up within the body try to restore the equilibrium position. So the applied force and internal elastic force are numerically equal, but their directions are opposite. So when external force is removed, internal elastic force is responsible for maintaining the original dimension. The dimension may be size, shape or both of the body. Now in other words, solid body is said to possess the property of elasticity of volume and elasticity of shape. Now let us see some example of elastic material. We can say spring, rubber, and there are some more examples also. Now next property is plasticity. Plasticity is the property of a material to undergo a permanent deformation even after removal of external deforming forces. Means let me explain this. Suppose I have some body, I am applying some force on it. So it will get deformed, means its dimension will change, whether it is size or shape or both. Now I will remove the force. So even after removing the force, the deformation will be permanent. The example of plastic bodies are Dove and we can say the plaster of Paris and all. So the bodies which do not regain their size or shape, we can say the original dimension after removal of deforming forces, are called plastic bodies. These bodies can be deformed to a large extent by a small deforming force. Means for a small application of force, there is larger deformation. As such, no body is perfectly elastic or perfectly plastic or perfectly rigid. The example we can consider here, clay, then plasticine and putty are the examples of the plastic bodies. Perfect plasticity exhibited by a certain material is its property to undergo irreversible deformation. Irreversible means we can't reverse the process. So without any increase in load. So let us see what is mean by deformation here. I'm taking the name of word that deformation. What is deformation? Most of the bodies can be deformed by application of suitable external force. The change in size, shape or both of the body arising due to external force is deformation. Deformation is a basically change in size, shape. In general we can say it is change in length or area or volume of a body because of application of force. So the force which is responsible for this deformation of the body is called deforming force. So in general, deformation is proportional to definitely deforming force. The value of force means larger the value of deforming force, larger will be the deformation. Now let us consider the similar concept here. There are many ways in which deformation may take place. Means we can deform the body in different ways. We will discuss 3 ways here. First, we can change the length of wire or cord. Second, change in volume of a body. And third, change in shape of the body. So when deformation of body takes place, the body is said to be a strained condition. Body is said to be in strained condition or deformed state. Means we can say that body is under strain. So when let's take example, when a rubber cord or a metal wire is stretched, its length increases. As you know, the wire regains its original length after removal of applied force. So when an inflated volleyball bladder say is pressed by hands, there is change in its shape and volume. You must perform this particular activity in your childhood. So as soon as we remove our hands, the rubber bladder of the volleyball regains its original volume and shape. So in the deformed state, the applied force numerically is equal to its internal elastic restoring force within a body, but it is in opposite direction. Thus deformation produced in a body is due to change in relative position of molecules within a body.
No more spending your energy and money on coaching classes or missing classes for rain, for rally and any other nonsense. Subjects covered by multiple teachers with repeat telecasts. Doubts, concepts, applications, no problem. All explained through great and significant animation. So sit back comfortably in your home and watch Study Spectrum TV channel.
Now here we will consider this deforming force or internal restoring force in the form of stress and strain. So let us see what is stress and what is strain. The elastic properties of the materials are expressed in terms of stress and strain. So stress is defined as internal elastic restoring force per unit cross-sectional area of a body. Means it is force created by a unit cross-sectional area of a body to oppose the motion, or it is opposition caused by unit area of a body for any kind of displacement or a movement. Now in equilibrium, the applied force and internal elastic restoring force are numerically equal but opposite in direction. However, the stress we can define as, stress is defined as applied force per unit cross-sectional area of a body. Strain is internal restoring force and stress is applied force. So we can write here stress is equal to applied force upon area, so which is also equal to elastic restoring force upon area. So here the unit of stress is Newton per meter square, because see, the stress is applied force upon area. So unit of force is Newton and area is meter square. So the unit of stress becomes Newton per meter square, or just we can say Pascal, and its CGS unit is dyne per centimeter square, and you can find its dimension. You will find it is equal to L raised to minus 1, M raised to 1, T raised to minus 2. So now let us see the types of stress. First type, longitudinal or tensile stress. Now let us discuss this. When applied force or deforming force produces change in length of a body, means here only length is changed. We can say we are changing length of wire or beam, etc. The stress associated is called longitudinal stress or tensile stress. We are creating tension in the wire, so we are calling it as tensile stress or longitudinal stress, and this is deformation in length only. So when let us solve equation for it, means let us have an expression for the stress developed in a wire. So we will say when a metal wire of length say capital L and radius small r is stretched by a load, that is applied force here we are taking as F, it elongates. You can see the figure. So now the elongation or extension produced in a wire depend on nature of material. Definitely which material we are taking, it depend on that. So stretching force or cross-sectional area and original length we can write thus: longitudinal stress or tensile stress is equal to applied force upon cross-sectional area. So in general we can write F upon A, where F is force and A is area, cross-sectional area of the wire. So F upon pi r square, since the wire have circular cross-section. So now here my F will be mg, that means that load that we are applying here. Suppose I am applying, or suppose I am tiding the mass of capital M and we are pulling that string due to gravitational, means gravitational acceleration, that is g. So my F becomes mg upon pi r square. So this is the required equation, and you can see, suppose in the figure we will describe some quantity. Let's capital L be the original length of metal wire, and capital L plus small l is length of wire when there is applied force, means after application of force. So let us say the elongation in the wire is small l, so total length of wire become capital L plus small l. Now L, as I already mentioned, it is extension or elongation produced. F is applied force, or we can say load, and pi r square is cross-sectional area of the wire. So now the second type of stress developed is volume stress. As the name suggests, it is deformation in volume of a body. Now this is very important. Let us have a look. If a deforming force produces change in volume of a body, the stress associated is called volume stress. Now when a block, means we can say, we can take here a rubber box or a cubical shaped body. So we are applying force on it and volume of the body is changed here. So when a block of rubber having volume say capital V is subjected to additional pressure. Now here force is in the form of pressure, that is applied force is in the form of pressure. That means we are applying pressure here from all the sides, then its volume decreases. This you can perform with eraser also. This is very simple experiment. Here in the figure you can see there is one cubical shaped body. We are applying force in the form of pressure, say small dp, from all the sides. So because of that its volume is decreased. Say the change in volume is dV. So we can mention here V, capital V was my original volume. Now V minus dV is final volume and dV is decrease in volume. So volume stress we can write it as applied force upon area. So as you know, for pressure is force upon area, that is for force we can write pressure into area. So here we can write A, capital A, that is area, into dP, that is applied pressure, upon area of the cube, area of that particular material we are taking here. So area get cancelled and we get the volume stress as dP. So you can say volume stress is nothing but applied pressure here. Third type of stress is shearing stress. Now this is very important stress and examples are asked based on this particular stress. So let us see. It is little tricky but easy to understand if you pay attention carefully. Now if deforming force produces change in shape of a body, the stress associated is called a shearing stress. Means here we are changing shape of a body. Remember in the volume stress, shape was not changed, only the volume was changed. So now let us have a look at figure. When a tangential force F is applied to a top surface EFGH of a cube ABCDEFGH, whose bottom surface, that is ABCD, is fixed. Now its shape changes to a parallelopiped ABCD, E dash, F dash, G dash and H dash. Now here ABCD is fixed. Here we are applying a horizontal force only at the top surface so that its shape is changing. So we can write the expression for shearing stress as tangential applied force upon area, that is general expression F upon A. Now here according to geometry we can write, as you can see here we have mentioned, it is having a displacement of angle theta. So we can write the expression for this particular change here. It is F upon say A theta. So let us derive that expression. Here ABCD EFGH is original shape of cube and ABCD E dash F dash G dash H dash is new shape. F is tangential force applied to top surface EFGH. So E dash F dash G dash and H dash are lateral displacement of upper layer. So here in this particular syllabus the perfect expression for shearing stress is not obtained. So these are the three types of stress: longitudinal stress, volume stress and shearing stress. Now we will see the strength. Now let us define strength first. Strength is defined as the change in dimension per unit original dimension. It is very simple. Stress was applied force upon area. Now this is change in dimension per original dimension. So strength is dimensionless since it is a ratio of the similar quantities. So it has no unit. So let us see type of strengths. First type is again longitudinal or tensile stress strength, similar to longitudinal or tensile stress. So if the applied force produces change in length of a body, say metal or wire or beam, then strain associated is called longitudinal or tensile strain. Here in this particular type of strain, we are taking the change in length to its original length, means here we are considering only one dimension, that is change of length. So longitudinal or tensile strain is defined as ratio of change in length to its original length. So let us write, so longitudinal or tensile strain is equal to change in length upon original length. So we can write final length minus original or initial length upon original length. So if my final length is say capital L plus small l, that is my final length, minus my initial length was capital L upon, so original length capital L. So capital L get cancelled from numerator and you get the longitudinal strain as small l upon capital L. Now second type of strain is volume strain. So if the applied force produces change in volume of a body, the strain associated is called volume strain. So volume strain is defined as ratio of change in volume to the original volume. So we can write volume strain is equal to change in volume upon original volume. So if my change in volume is dV, so we can write minus dV upon V. We are giving negative sign because there is decrease in volume. So volume strain is dV upon d if we are taking only its magnitude. So the third type here is shearing strain. If the applied force produces change in shape of a body, the strain associated here is called shearing strain. So similar shape we are considering here. When a spiral spring is stretched, wire is not extended but is twisted or sheared. The extension produced in this case depends on shear modulus and dimension of the spring. So for this shearing strain, we can write the expression according to figure. Firstly, let's just have a look in the figure. You can write. So the shearing strain is defined as the ratio of relative displacement of any layer to its perpendicular distance from a fixed layer. Now here we will consider the same diagram that we considered at the time of finding shearing stress. Now shearing stress is equal to angle of shear. You can see the angle theta in the figure. This is the angle of shear. Now let's see how we obtain this. So shearing strain we can write relative displacement of any layer upon its distance from the fixed layer. So shearing stress from the figure we can write E dash upon dE, F dash upon CF, or G dash upon BG, or H dash upon AH. Now we can see from trigonometry, this is tan theta. This is the value of tan theta. So as if theta means displacement is very small, tan theta is approximately theta. So here for shearing stress we get the expression as theta, and theta is measured in the form of radians. Now shearing strain is also called shear. So this is shear theta in radians. Now here is one law we will consider here which gives the relationship between stress and strain. It is known as Hooke's law. So let's see. Robert Hooke, from means the time span of this scientist was from 1635 to 1703, and he was inventor and astronomer, surveyor, and also physicist from UK, and has given fundamental law of elasticity. So from name of the scientist, this is known as Hooke's law. So in other word, Hooke, the law ut tensio sic vis, which means as the extension, so the force. Means if there is extension, that means there is a force. So we will see this in details. We come across Hooke's law behavior in many cases of bending, twisting, stretching, compression, that is all varieties of deformation. Means from all these of deformation we can derive the expression for Hooke's law, or we can verify the Hooke's law. So here let us consider one experiment. The material which obey Hooke's law are termed as linear elastic or Hookean material. Here in the diagram you can see one figure, means one graph is given. According to this graph, on y-axis stress is plotted, on x-axis strain is plotted, and you can see this is a straight line. It is giving the straight linear relationship between stress and strain. It is, means we can say from this figure that provided the elastic limit is not exceeded, the deformation of a material is proportional to force applied across it. Let me explain this. Provided the elastic limit is not exceeded. Elastic limit means for a particular material there is elastic limit. Means see, suppose I am having one wire, I am applying force. After removing the force, it will regain its shape. We will do this by increasing the forces by quantity, say by 5 newtons or 10 newtons. So there will be a limit, means for a higher value of a force, when that value of a force is reached, when that force is applied and removed, the length of the wire will not regain. That means its elastic limit is crossed. Means there is a particular limit for which wire can handle that force to regain its original length. So the definition or the Hooke's law was where means up to the point where elastic limit is not crossed, elasticity regain or elasticity we have in the wire is proportional to applied force. So thus from the figure we can write stress is directly proportional to strain. So stress is equal to m into strain. Here m is proportionality constant and is known as modulus of elasticity. For m we can write stress upon strain. So modulus of elasticity is the ratio of stress to strain for a particular material. Now since stress is directly proportional to strain, the graph of stress, which is plotted on x-axis, against the graph of strain, which is plotted on x-axis, is straight line passing through origin. As you can see, the slope of the graph gives modulus of elasticity, that is our m value. Thus the modulus of elasticity of material is defined as slope of stress strain curve. This is called stress strain curve in elastic deformation region. Elastic deformation region means here we are not exceeding the elastic limit of the wire. Now the modulus of elasticity depends on firstly the nature of the material, and also we are not exceeding the elastic limit here. The maximum value of stress up to which stress is directly proportional to strain is called elastic limit. Means here again they have explained what is elastic limit. Means suppose we are performing an experiment. Suppose I have a wire of length 1 meter and I am applying load across it. Suppose I am applying 500 grams, then 1 kg, then 1.5 kg, 2 kg and all. I am doing the experiment. For this, at the same time I will plot the graph. Means I will plot the graph of length versus applied force. So you will have a straight line. A point will come where for the application of the force, means suppose I am applying the force of suppose 10 to 15 kg, the linearity of graph will disappear. So we will say that the limit, that is elastic limit, is exceeded, means there will be no regain of length of the wire, there will be smaller permanent deformation in the wire. So here the means the region of the graph where stress is directly proportional to strain is the elastic limit. So the permanent deformation that I was calling here is known as set. Means suppose I was performing experiment with 1 meter long wire. So when elastic limit is crossed, suppose now I am measuring the length after removing all kinds of loads. My length is now, it is 1.15 meter. So 0.15 meter is set in the wire. So since stress is dimensionless quantity, SI unit of modulus of elasticity is similar to stress, that is SI unit of stress is Newton per meter square, and dimension will also same, that is L raised to minus 1, M raised to 1, T raised to minus 2. Now here we will consider some elastic constants. Let's see, there are 3 kinds of stress and 3 kinds of strain. Means we are considering here length, change in volume and change in shape in these 3 particular stress and strain. Hence corresponding to each type we have 3 types of elastic constants. This is very simple. We will just take ratio of that particular stress to that particular strain. So let us consider our first constant. This is known as Young's modulus, and this is related to length. That's why it is elasticity of length. Now let us see this. The modulus of elasticity related to change in length of a body such as metal wire, beam, etc. is called Young's modulus of elasticity, named after a British physicist Thomas Young. Now Young's modulus measures the resistance of an elastic solid to elongation and is typically used for characterizing a rod or wire subjected to compression or tension. Let us have a look how this modulus, how this Young's modulus is obtained. The value of Y depends on nature of material. If a material has large Y value, means it has large Young's modulus, it resists elastic deformation and large stress is required to produce a small strain. That means you can say up to 80 to 90% the material is rigid here. So Young's modulus is very important in engineering. Young's modulus for material with strong interatomic bonds is high. We can say for solids. Now Young's modulus is the ratio of longitudinal stress to longitudinal strain. Now we will derive expression for Y. Now consider a metal wire of length L, radius small r, suspended from a rigid support. So now let the wire is to be subjected to load, say mg, which is attached at the free end of the wire. Now when a deforming force is applied, that is mg, to a body in one direction, let us say the change in length takes place, and the final length of the wire we can say capital L plus small l, and then L is called extension or elongation in the wire. So longitudinal strain is change in length upon original length as we defined earlier, so it is small l upon capital L, and the longitudinal stress will be applied force upon area. So we can write mg upon pi r square. So let us divide them. So we can write Young's modulus is equal to longitudinal stress upon longitudinal strain. So Y is equal to mg upon pi square upon L, small l upon capital L. So after rearranging the term, y we get it as mg into capital L upon pi r square into small l. Now here the SI unit of Young's modulus is Newton per meter square, which is the unit of stress only, and its dimension will be similar to stress again, L minus 1 m1 t raised to minus 2.
No more spending your energy and money on coaching classes or missing classes for rain, for rally, and any other nonsense. Subjects covered by multiple teachers with repeat telecasts. Doubts, concepts, applications, no problem. All explained through great and significant animation. So sit back comfortably in your home and watch Study Spectrum TV channel.
Now here let me mention Young's modulus of elasticity is elasticity of length. Since only solids have certain length, Young's modulus is property of solids only. We can't consider Young's modulus for liquids or fluids. So now second constant is bulk modulus. It is denoted by capital K, and this is volume elasticity. Now the modulus of elasticity related to change in volume of a body due to applied deforming force is called bulk modulus of elasticity. This modulus of elasticity is related to change in volume. So definitely, as the previous concept, here also we will divide volume strength to volume stress. Now let us see how to obtain the expression. Here we will see bulk modulus is defined as the ratio of volume stress to volume strength. Now bulk modulus measures the resistance offered by a liquid or solid while an attempt is made to change their volume. Means this is opposition caused when we are trying to compress them. So consider a rubber cube having volume capital V. Let it be subjected to additional pressure, say dP, or force F applied perpendicular to its surfaces from all sides. You can see the previous figure of that volume stress. Now consider V minus dV is the new volume of a rubber cube, and increase in pressure by amount dP produces decrease in volume by amount of dV. So volume strength is change in volume upon original volume. So volume strength is minus dV by V. Now volume strength is equal to dV by V. Numerically we are taking modulus only, we are removing negative sign. Now volume stress is change in pressure, that is dP. So bulk modulus is volume stress upon volume strength. So dP upon dV upon V, that is K is equal to V into dP upon dV. So bulk modulus of elasticity is a property of solids, liquids and gases, all the three. The SI unit of bulk modulus is again Newton per meter square. Dimension is also similar, L raised to minus 1, m raised to 1, t raised to minus 2. Now the reciprocal of bulk modulus of elasticity is called compressibility of the material. So compressibility is 1 upon bulk modulus. Now by this factor compressibility we can find the value of compressibility of the material, means up to how much extent we can compress the particular material. And here SI unit of compressibility will be meter square per Newton, and dimension will be L raised to 1, m raised to minus 1, t raised to 2. Now our third type of modulus is modulus of rigidity. It is shown by one particular symbol, you can see it is known as eta, and this is elasticity of shape. Now the modulus of elasticity associated with changes in shape of a body is called modulus of rigidity. Modulus of rigidity measures resistance offered by a solid while an attempt is made to change its shape, that is motion of planes of a solid sliding past each other. Now consider the same diagram from the previous one that we had considered during the stress. Now consider a cube ABCDEFGH whose bottom surface ABCD is fixed and a tangential force F is applied to its top surface EFGH. Now shape of the cube changes due to application of force and it become parallelopiped ABCD, E dash, F dash, G dash and H dash. Now let us write down the expression for shearing strength. It is relative lateral displacement of layer upon distance from a fixed point. So shearing stress we obtained as tan theta that we had obtained previously. So for a particular, means for a small variation, for a small angle theta, we can write shear or shearing stress as theta and shearing strain as theta, and now shearing stress is force upon area, that is F upon A. So modulus of rigidity is defined as the ratio of shearing stress to shearing strain. Thus the modulus of rigidity is equal to shearing stress upon shearing strain. So it is F upon A upon theta. So modulus of rigidity, that is eta, is equal to F upon A theta. Now this is the required expression. Now these are the three constant, that is Young's modulus, bulk modulus and modulus of rigidity. Now here we have a new concept known as Poisson's ratio. It is denoted by sigma. Now let us see what is Poisson's ratio. When a force is applied to a body along any direction, there is change in size along the direction of force and change in size perpendicular to the direction. Now if force is applied to the free end of a metal wire, it gets elongated, that means its length is increased. This is accompanied by decrease in diameter of metal wire. Definitely length is increasing so that its diameter, that we can say the area of cross section, is decreasing. So in other words, longitudinal extension is accompanied by lateral contraction. So this lateral contraction depends on the nature of the body and proportional to size, direction as well as the stress. So this proportional change is called lateral strain. So now we will obtain particular expression relating all these quantities. So within an elastic limit, lateral strain is proportional to longitudinal strain. So lateral strain is directly proportional to longitudinal strain. So lateral strain is equal to sigma into longitudinal strain. Now here sigma is constant of proportionality called Poisson's ratio. So we can define Poisson's ratio is equal to lateral strain upon longitudinal strain. So for homogeneous isotropic material, the value of sigma lies between -1 to 0.5. This is the value of Poisson's ratio. Now in actual practices, sigma is always positive, means that experiment we are performing, for that sigma is always positive and we can find between 0.2 to 0.4. Now the example we will see here, Poisson's ratio of cork is 0, that of metal is about 0.3 and that of rubber is nearly 0.5. Now Poisson's ratio is unitless and dimensionless quantity, since we are taking the ratio of similar quantity, and Poisson's ratio is defined as ratio of lateral strain, that is transverse strain, to the longitudinal strain. Now here we will perform an experiment to find out Young's modulus of the particular wire. So let us see the experiment. This is the topic, determination of Young's modulus for a wire. Now you can see the figure. This figure illustrates a typical arrangement For determination of Young's modulus of a material wire, two long straight thin wires, you can see P and Q, of the same length and same radius and same material are suspended side by side from a rigid support S. The wire P is called reference wire. It is kept taut by a weight W attached to its lower, that is free end, and carries a scale M graduated in millimeters. The wire Q, so called experimental wire, carries a pan in which known weight can be placed, means we can place the weight 5 kg, 10 kg and all. Vernier scale V is attached to the bottom of experimental wire, whereas main scale M is fixed to reference wire. This is shown in figure very clearly. You can see that. Now when weights are placed in the pan attached to wire Q, this is experimental wire for which we have to obtain the Young's modulus. Now load is increased, which therefore increases force F in the wire, means we are increasing the applied force. The elongation is produced in wire Q. Because of increase in forces in experimental wire, the elongation produced in experimental wire is measured by vernier calipers V. The reference wire is used in order to compensate change in length that may occur due to change in temperature, that is the increase in length of reference wire and experimental wire due to change in room temperature is the same. So now for a reference wire we are using here to remove the error caused by change in temperature. Now both the reference wire and experimental wire are sufficiently loaded in order to make wire straight and tight, and vernier reading is noted. Now the experimental wire Q is gradually loaded. Gradually means we will increase the load step by step in order to bring wire under tensile stress. Now every time vernier reading is loaded means I am increasing the load, noting the reading, increasing the load and noting the reading, like that. So the difference between the two vernier readings gives elongation produced for that particular load. Now if small r and capital L be the radius and length of the experimental wire Q initially, here the area of cross section of wire Q is pi r square. Let small l is the elongation, that is increase in length of wire Q. Now when say mass M, capital M, is attached to lower end, which is a free end of wire Q, that is extension or elongation produced in the wire is given as, so small l is the extension in the wire. So for this particular wire, if I am taking mg as applied force, where g is acceleration due to gravity, we can write by definition Young's modulus is equal to longitudinal stress upon longitudinal strain. So as you know, longitudinal stress is mg upon pi r square and longitudinal strain is small l upon capital L. So let us substitute the values and you will get the expression mg into capital L upon pi r square into small l. So measuring extension, that is small l, radius r, small r, original length L, and noting the load Young's modulus can be determined. So by using this experiment we can determine the Young's modulus of the wire. Now we will see behavior of a metal wire under increasing load. In this particular case, lastly we have performed experiment with P and Q wire. That same experiment we will plot one graph, and according to this graph we will study the behavior of wire. Now the behavior of metal wire subjected to increasing load can be studied by using Seal's method. A load is applied to the wire in step of half of kilograms until the wire breaks. That means we will go on increasing the load by half of kg till the wire breaks, and at the same time we will take the reading of the length of the wire. That means we will find stress as well as strain, and along with we will plot the graph. Now elongation in the wire is measured. Now we plot the graph of stress along y-axis and strain along x-axis. Then the nature of graph you will get like this, that you can see in the figure. Now look at this graph carefully. Along the x-axis you can see it is tensile strain, and along the y-axis it is tensile stress. Now here origin is O. You can see up to point P it is straight line. Then from point P to point E again it is a straight line part, and from E to E dash there is a particular variation, and the variation is continued and it is up to point B. Now let us see. Now here the quantities in the graph are E is elastic limit, point E denotes elastic limit, OS is permanent set. As I defined earlier, let me explain you again. Set is a permanent deformation created in the wire. That means it is that point for which if we remove the load, then also there is a permanent elongation of particular quantity in the wire. Lastly, I had explained one example. I was performing experiment with 1 meter wire, and for a particular value of load the elongation was 0.15 meter, which was a permanent set. Now here YP is yield point, that is plastic flow begins. I will explain you later what is this yield point. N is breaking stress and B is breaking point. Now initial part OE, as you can see in the graph, it is a straight line and it denotes that stress is directly proportional to strain. Means up to this point Hooke's law is obeyed. It is up to point E. The value of stress corresponding to value of E is called elastic limit of material wire. Now if load is applied to wire is removed, the wire completely regains its original length. Means within the elastic limit wire regains its shape. Now point E represents the limit of proportionality between stress and strain. Now after this point also, if the stress is increased beyond point E, the graph is no longer a straight line and Hooke's law does not hold good. In this case, for a small increase in stress, the strain increases faster and graph bends towards the strain axis. That means for a small increase in load, the elongation in the wire will be larger. Now if the wire is straightened up to E dash beyond point E, and then if load is removed, the wire is unable to cover its original length. However, wire retains its elastic properties, means the wire having elongation, but we can perform the experiment with that wire. The strain OS remain permanently set in the wire, so this is the value of set. Now if wire is loaded again, we get straight line graph S E dash, you can see in the figure. Means we will repeat the whole experiment, we will have the similar graph because wire is having set but it is still an elastic wire. So now strain OS is called set. Now if load is increased further, we get point YP at which the tangent to the curve become parallel to strain axis, as you see in the figure. So this means that extension begins to increase even without any increase in the load or stress. Means we are not putting any kind of load, then also there is continuous increase in the length of the wire. So this is the point of flow called as plastic flow. Means wire is deforming. At this point elastic wire is showing the property of, say, plasticity. That's why it is plastic flow. So the yield point YP is called means YP denoted point is called yield point. The value of stress corresponding to yield point is called yield stress, means that we can measure from y-axis, it is yield stress. Now for further experiment, yield point, the curve begins to bend upwards and the portion YPN of the graph is obtained. As at this stage, when wire or material begins to flow, the cross section of wire decreases uniformly up to end. Later, neck or constriction begins to form at a weak point, and the point N represent the maximum stress which wire can bear and is called breaking stress. This is a point which giving us the value of load that wire can handle. For further load, wire will break. So once the neck is formed, the wire begins to this out locally, where the strength increases faster even though the stress is decreased, and the wire finally breaks at point P. Let me repeat this. Once the neck is formed, the wire begins to thin out locally, means it getting thinner and thinner, and when strength is increased faster even though the stress is decreased. Even though we remove the all kind of load, wire gets thinner and point B comes where the wire breaks. So this is the breaking point. The substances which lengthen considerably and undergo plastic deformation till they break are called ductile substances. That means lengthens considerably means we can increase their length. So these substances are rough iron, copper, lead, etc. And substances which break just after elastic limit is reached are called brittle substances. For example, glass, then high carbon, steel, etc. Now ductility is an important property that allows metal to be drawn into wires. Metals are malleable and useful engineering materials. So because of strength, malleability and ductility property. Here in this particular chart, you can see the values of ductility are given here. You can see all the materials having breaking points in this particular figure. Here we will see the relationship between Young's modulus, then coefficient of linear expansion and thermal stress. Now consider a metallic rod of length say L0, small l0 at theta degree Celsius. Now if the temperature of rod is increased by say suppose delta theta, then final length of the rod is given by expression small l is equal to L0 in the bracket 1 plus alpha delta theta. Now where alpha is coefficient of linear expansion of the material of the rod. Now here linear strain is change in length upon original length. So linear strain is equal to L minus L0 upon L0. Now from the equation L is equal to L0 in the bracket 1 plus alpha delta theta, we can substitute here L minus L0 upon L0 is equal to alpha into delta theta. For left hand side we have substituted the value. Now stress is equal to y into strain, which is Young's modulus. Stress can also be written as y into alpha into delta theta. So now force exerted by rod due to heating, therefore it is equal to thermal stress into area. So it is y alpha delta theta into A. So this expression here is given directly. There is no particular derivation for this. This is a smaller topic. Based on this topic, we will have few sums. We will solve that later on. Now our next topic is application of elastic behavior of material. What are the application of elastic materials basically that we will see here. Now elastic behavior of materials has a wide spectrum of application in design of bridges, construction of homes and malls, in machinery, in industry and so on. In design of building, a civil engineer has to take into account strength, nature of material used in columns, beams and supports. That you can see we have flyovers. Building those particular flyovers, the engineer has to consider these quantities. Now, as you know, cranes are used to lift and move heavy goods from one place to other. To lift an accidented vehicle which has fallen in river, valley, etc., cranes use heavy metallic ropes to which load is to be lifted is attached. Now rope is pulled by motors and wound over pulley. The thickness of such ropes in cranes is decided on the basis of elastic behavior of materials of the rope along with factor of safety. That is, let us take example. Suppose a truck carrying goods with a total weight of 10 ton has fallen in a valley in a road accident. Now 10 metric ton is 10 into 10 raised to 3 kg, which is 10 raised to 4 kg. Now we may not attach a load more than this, so we can write here the value of the particular material. However, rope is designed for a factor of safety, that is 10. So we should not break even the load to be lifted is 10 into 10 raised to 5, means actual load is 10 raised to 4. Now for a safety purpose we will take the load 10 raised to 5 Newton. So the ultimate stress is equal to 10 into 10 raised to 4 upon pi square. You can say here applied force, here we are considering 10 into 10 raised to 4, and pi r square is definitely cross-sectional area of the rope. So the ultimate stress should not exceed the breaking stress. The breaking stress is 5 to 20 into 10 raised to 8 Newton per meter square, as well as elastic limit for that particular rope is that rope is made up of steel, so that's why it is YS, that is Young's modulus for steel. So it is 30 into 10 raised to 7 Newton per meter square. Now ultimate stress is taken as a measure of tensile strength of a material. So thus we can write 10 into 10 raised to 4 upon pi r square is equal to 30 into 10 raised to 7. So pi r square is equal to 0.3333 into 10 raised to minus 3 meters square. So this is the area of cross section. So area of cross section should be greater than or equal to W upon YS. So W is weight of the load. So A should be greater than or equal to 10 raised to 5 upon 30 into 10 raised to 7. So it is greater than 3.333 into 10 raised to minus 4 meters square. So our radius of rope must be greater than or equal to 1 centimeter. So in order to have flexibility to rope, it is made up of large number of thin wires braided together, that you can see in the figure. Now bridges are designed for convenience and to withstand the load of traffic, that we are considering flyovers here. Now bridges are under tremendous stress due to weights they are supposed to support. Now here also the vehicles are moving on bridges, so we can't say that the load is constant on bridge, it is also moving. So bridge may be of suspension type or arc type. Suspension bridge supports its load through tension in cables and compression in towers, whereas an arced bridge is one which supports load primarily through compression, that you can see in the figure both type of bridges. In construction of buildings we use beams and columns, that is very common. Now in both the cases bending of beam under a given load is important. So Young's modulus is used to calculate deformation of loaded structure and its parts. Now consider a horizontal beam support at its two ends. The beam sags under its own weight. Due to this, top of a beam is under compression and bottom of a beam is under tension. So this can be minimized by giving top and bottom of a beam a larger cross-sectional area that you can see in the figure. Since there is neither compression nor tension along the center line of the beam, this part has a smaller cross-sectional area, means length is smaller. So bending of a beam stretches some fiber and compresses other. So hence Young's modulus is involved in bending also. Now what I explained, you can see in the figure the horizontal as well as vertical figures of the bridges. Now we will see the figure. You can see in the first figure there is horizontal beam is given which is compressing. So upper area is having compression, lower area is having tension, and it is in the second figure it is having some kind of weight. So now suppose for the first case, beam is supported at both the ends, is under compression and tension, and in the second case beam supported at two ends and loaded at some center, that weight is W. Now consider a steel bar of length L, breadth B and depth D loaded at a center by load W. Then the sag, that is it is eta of CG, that is center of gravity or bending of beam, is amount that is delta is equal to W L cube upon 4 BD cube into Y. Now here first case, sag, that is delta is inversely proportional to D cube, it is inversely proportional to B, it is directly proportional to L cube, inversely proportional to Y. So since delta is inversely proportional to Y, one is supposed to use material having larger value of Young's modulus. Thus bending of the beam can be minimized using this material with larger Young's modulus. Small value L and large value B, means breadth and depth should be greater, length should be lesser, and higher Young's modulus value means the material is 80 to 90%, we can say material is of rigid, means rigidity factor is more. Now if a load is placed exactly at center of the beam and depth of the box is increased, then beam will bend as shown in the figure. So this is called buckling. To avoid this, cross-sectional shape of a beam or bar resembles letter I. It is shape of I, that you can see it is below the flyover used. Now the I beam minimizes both weight and stress, and I beam can be much lighter but almost as strong as for bending. So I beam has a large load bearing surface which prevents buckling, and it's enough to reduce too much buckling. Now I beam provides high bending moment and lot of material is saved. Now hollow circular pole or a tube resists to bending in all direction. That circular pole of some mass but smaller radius, since it has a greater effective cross section.